Hi guys, we've been going along with the moment with the equilibrium for a seesaw for a long time, and we're going to add the last complexity, that is, what if the distance given and the force are not at the right angles. And I want you to get a feeling for what is going on, so I want you to basically join me with an exercise, a physical exercise, and you need something that is heavy, for instance a dumbbell, or you could also just grab a heavy bag or something like that. And what I want you to do, I'm going to make a full screen so you can see me, and I'm going to stand up a bit. The dumbbell, first of all I want you to have it up over here, and then I want you to slowly go down, and I want you to feel when it feels the most heavy, and then go back up. Okay, now we're going to stop, put it to the side, and then what are we going to see? What we felt? Well, I felt that when my arm was at right angles with my upper arm, or underarm right angles with my upper arm, it felt the most heaviest. But the weight of the dumbbell didn't change. The force due to gravity did not change. The length of my arm did not change as well. So apparently there is something with a direction involved. And basically, if it's up here, you don't feel that much. Here in your biceps, basically nothing. It is almost relaxed. And if it's at right angles, you need to use your biceps. And that means that if the distance given, the underarm, and the force is not at right angles, you get something different. So basically, if I have my arm, I'm going to scribble a bit over here. This is my upper arm, and here is my bicep, and then over here is my biceps, and here is the dumbbell. Then right now, if it's at right angles, then the turning force of which I feel is the greatest, and if I have the same but it goes up a bit, then the turning force is lower. So apparently if it is not at right angles, it becomes lower, the turning force or the moment. Well, how does it work? Well, we need something that is called the line of action. And if we go to the blue part over here, then you can see that the force goes down, and the line of action is the line through the force. This is the line of action. And then the arm is the distance from the fulcrum, and of course your elbow is the fulcrum, to the line of action. This is the longest arm you can get with your own arm. And then if we go to the red bit over here, then if we draw the force and then the line of action, gravity always goes down, guys, so the line of action is always vertical if you have gravity, and then the arm is the shortest distance from the fulcrum to the line of action. You can see it's a shorter arm, so then the moment is the force multiplied by the arm is smaller. And you can see that direction is what is needed. So basically, what is there if we're going to calculate, or we're going to use a moment, or there is something that is balanced and it can rotate, we're going to use these steps. You might not need to do all the steps, but you do need to make sure you have them all in your calculation. First step, you need to draw the force or forces. Second step, you need to draw the fulcrum. Third step, you need to draw the line of action. And after you have drawn the line of action, you can draw the arm. Sometimes you need to measure it, but sometimes it's given. And then you can calculate. If you need to calculate the moment, then you use the formula that the moment is the force multiplied by the arm. Or if there's equilibrium, then you calculate with force 1 multiplied by arm 1 is equal to force 2 multiplied by arm 2. And just to be sure, you need to make sure in your notes you have the fulcrum, the point around which it rotates, and the line of action, the line through the force. Oh, please erase the E over there. I mistyped that. And the arm, it's the shortest distance from the line of action to from the fulcrum to the line of action. It's always at right angles with the line of action. So this was the shortest distance from the line of action to the fulcrum, and it is at right angles over there. Okay, how do we use this? This is, for instance, you can see these guys when they want to block a road, so a road blockage. And in the Netherlands, they might be automatic, or there is no one standing next to it. But if lots of people need to go through it, then it's automatic. But in India, and I think Mr. Mulder can agree, he was over there, but if not, I stand corrected. These roadblocks, they simply have policemen operating them, and they have a rope, and to make it easy to operate them, you have a counterweight over here. And this guy is just pulling on the rope if it needs to close, or letting the rope go when it needs to open. And in this situation, well, basically need to know what the force of the guy is over here. We're not going to do the total calculation, but we're going to do the steps just before the calculation. Okay, so we are going to ignore the mass of the pole because this is very heavy over there, and the counterweight makes it a bit easier. So first of all, we need to draw the forces, and I'm going to do that in red over here. First of all, the guy pulls in the direction of the rope, so this is one force. And the counterweight is a force due to gravity, so it goes down. Okay, after you drew the force, you need to draw the fulcrum. So that is over here. So there's the fulcrum, just to make sure I put an F next to it. And I'm going to call fulcrum. I'm going to call this force F1 because it has a given name, and this force I'm going to call F2. Just need to give them names, else you are confused. After the fulcrum is to draw the line of action. The line of action is the line through the basically through the force. And wondering what color, I'm going to use blue for line of action. And so I'm simply going to draw a line, and you can extend the line as long as you want to, and it needs to go in the same direction as the arrow of the force. And then after the line of action, I can draw the arm, and it needs to be at right angles. So I'm just going to grab a geo. This is my nice geo, and as you can see, you can simply move it around a bit, and first of all, the arm of F1, that is to the left, it needs to be at right angles. So I'm simply going to throw it, and then over here we have one arm. I'm going to make arrows out of it. So this is one arm, and it is at right angles. And this then is called R1 for arm 1. And on the other side, and I need to rotate my geo, that it is at right angles with the other line of action, like this. down just a bit more. There it is. And then I need to make sure it goes through the fulcrum as well, like this. And then the other arm, or effective distance, but the book uses arm, is this one. And I'm going to make it into a pen. Where are they? Going to take it in, make it nice. So this is R2, arm 2. Oh, make it away. Oh, and then if you cannot find the actual numbers in the drawing, if you need to, then you need to measure it. So you need to grab your geo again, and then you simply place it next to your arm, and you're going to measure it. So for instance, over here, as you can see, the this arm is then 7.5 centimeters, and then we're going to measure the, and you can simply use your geo to measure the other one, and that is then 1.7. So you simply can write it down, 1.7 centimeters, and the other one was 7.5 centimeters, and then we can calculate if it's in equilibrium with this formula. If we know one force, then we can calculate the other one. Okay, we're going to practice this in class. See you on Wednesday, and till then, bye bye.